All right, so this problem says a conductor carries a current that is decreasing exponentially with time. The current is modeled as I equal to I naught. So the current in this thing is I naught e to the power minus t by tau. This is called the time constant, and what that tells you is that's the time over which things change. So after one time constant, the current will be 35% the maximum current. So at t equal to 0, this is 1, that's the current. After one time constant, the current is 35% of this. Okay. And let me show you a circuit where this happens. Okay, so this is the circuit, the flash camera circuit, the pacemaker circuit, and everything. You close this switch. While this switch is open, the capacitor gets charged. And then once the capacitor is charged, you open the switch, you close this switch, and the capacitor discharges. And the current through this thing is exponentially decaying. Okay? So when you first close the switch, that's when the current is maximum. And then it exponentially decays. All right. So the current is modeled like that. I naught is 3 amps, so the initial current is 3 amps. And time constant is 0.5 seconds. So after 0.5 seconds, it's 35% of the original current. After another 0.5%, it's 35% of the remaining current, and so on. How much charge flows through the conductor between t equal to 0 seconds and t equal to 3 tau? Okay, I is dq by dt. Okay. What this is qt is the total charge that has flown after time t. Okay, and dq by dt is the amount of charge flowing at that rate at which the charge is flowing at that time. Okay, so that's the equation. And if you want to find how much charge flows through, you just integrate this from initial to final. Okay, so it dt from 0 through 3 tau. This, of course, integral of a derivative is just that function, qt q at 3 tau. How much charge has flown after 3 time constants minus q of 0. Q of 0 is 0. Okay, so when you close the switch, no charge has flown yet. And the left-hand side is So I've sort of squeezed all that in, but anyway. So Q of 3 tau after 3 time constants minus tau I naught e to the power minus 3 tau by tau minus e to the power 0 is 1. They tell you I naught is 3 amps, tau is 0.5 seconds, and this number is that number is 0.95. So 1.343 coulombs have flown in that time. Amperes is coulombs per second, and the second cancels. So in this problem, you were given the current and you found the charge. And in this problem, you're given how much charge has flown and you want to find the current. So the quantity of charge through a conductor is modeled as that. What is the current at time t equal to 3 seconds? By the way, so these are in coulombs, these per second square, and this is millicoulombs, so I'll write it without units. 4t to the power 4 minus t plus 6 into 10 to the minus 3, and this is in coulombs. So each term is coulombs. So this is coulombs per second to the 4. This is a second. This 1 is coulombs per second. Okay, that's the units. So the current at any given time is just dq by dt equal to 16 t cubed minus 1. Okay, so we want to find the current at 3 seconds. That's 27 times 16. So 431 amps. So they say consider a wire of circular cross section with a radius of 3 millimeters. The magnitude of the current density is modeled as J equal to CR square. Okay, so C is that 5 million. What is the current through the intersection of the wire from the center to 0.5 R? Okay, so here's the wire, and they tell you the current density goes as R square. So the further out you are, the current density is greater. Okay? So if you wanted to drive, there's zero current here, that's the current density, and you know, and okay. So the current density is like this. Okay. So they're asking you, what is the total current? What is the current through the inner section? What is the current through there? And you can see that there will be more current flowing in the outer half than in the inner half. Okay. So DI, so what we'll do is, now I'm going to draw an end-on view. Here's an end-on view. Since it has radial symmetry, so this is the current coming out, okay? We'll call this DI, current coming out through that ring. DI is JR, that is the current density at that location, times the area of that ring. Can anybody tell me what is the area of that ring? We'll call this thickness dr.
It's 3 millimeters squared minus.
It's 2 pi r, that's the length of the ring, times dr. The area of a rectangle is side times that, okay? So cut that in a strip and undo it, I guess so. So that's the current through that little ring. Okay, we want to find the current through all those little rings, going from R equal to 0 to 0.5 R. From 0 to 0.5 R. R cubed, so that's R cubed, so R to the power 4 . So that's the current. So the inners, the current in the inners part, so this is pi by 2 C R to the power 4, which is 0.5 R to the power 4. All right, let's put those in. C is 5 times 10 to the 6 amperes meter to the power 4, 0.5 to the power 4, and R was 3 millimeters. Okay, let's take this is 10 to the 12, and so that becomes 10 to the minus 6. So pi by 2, 5 into 0.5 to the power 4, 3 to the power 4 into 10 to the minus 6. That is 1.5 to the power 4. Amperes. Okay. So 40 amps is flowing through the inner part of the wire. Let's calculate the current flowing through the outer part. What do you have to do to calculate the current through the outer part? All you have to do is change the limits, and the limits would be from 0.5 R to R. Okay. And this will be, so it's the same value here. It's, there's the integral pi by 2c r to the power 4 from 0.5 R to R. Oh, okay, 600 microamps. And here it's 40 microamps, so not even 10%. Okay, so what we have shown is, so there's the cross section of the wire, and through here is 10% of the current, and 90% of the current is flowing. Okay. Now, in real wires, I believe DC current flows evenly through the wire, but as the frequency increases, AC current for high frequencies, it flows in the skin.
Why
But,
is that?
huh?
Why is that?
Well, it depends on the penetration depth and stuff like that. So, yeah. So this is relevant for very high frequency stuff. All right, so the current supplied to an air conditioner unit is 4 amps. The air conditioner is wired using a 10 gauge diameter wire. The charge density is that, see, 10 to the 29 electrons per meter cube. Find the magnitude of the current density and the drift velocity. Okay, so for part A, the current density is the current divided by the area of cross section. Okay, so 4 amps. Well, okay, R is the radius of the wire. And the radius is 1.294 millimeters. Okay, half of that is the radius. And this becomes 10 to the minus 6 coming on top. That becomes 10 to the 6. 4 divided by pi 1.294 square into 10 to the 6 amperes per meter square. Okay, so almost 3/4 of a million amps per meter square. I want you to find the drift velocity. Now the current density is given as that times the charge and its electrons that are carrying the current, and times the drift velocity. So the drift velocity is Jn over E. Amperes is coulombs per second, and this is 8.48 into 10 to the 28 per meter cube. And the charge is 1.6. And amperes is coulombs per second. So the coulombs will cancel. Oh, no, this is per meter square. Amperes per meter square. Current density is amperes per meter square. So you get meters per second for the drift velocity. All right, so let's take care of powers of 10. This is 9, and so that gives you minus 3. So that's 0.76 divided by 8.48 into 1.6 into 10 to the minus 3 meters per second. and that is a millimeters per second. So the drift velocity is okay, 500th of a millimeters per second. Okay. The diameter of a zero gauge copper wire is that. Find the resistance of a 1 kilometer length. 1 kilometer is from here to Embry-Riddle of such wire used for power transmission. Is resistivity L over area of cross section. Okay. Let's look up resistivity of copper. Copper 1.7 times 10 to the minus 8 ohm meter. Length is 1 kilometer, 1,000 meters. Pi r is 4.126 into 10 minus 3 meters. Okay, powers of 10, that's 10 to the minus 6, 10 to the, that becomes 10 to the minus 2, and 10, so 17. And the units, the meter square cancels with meter square, so you get ohms. 17 divided by pi into 4.126 squared. So essentially this is roughly 17. So 1 over pi is what you have, about 0.3 ohms. Okay, this says a resistor is connected in series with a power supply of 20 volts. The current measured is 0.5 amps. What is the resistance of the resistor? Again, this is easy. This is just plain old Ohm's law. V equal to I R. Ohms. Okay. Volts over amps is ohms. What is the maximum voltage that can be applied to a 10 kilo ohm resistor rated at 0.14 watts? So it can only dissipate 0.14 watts. Okay. Power is V times, okay. So power is V times I square R, or V square over R. So since we're finding the voltage, we are given this, so we'll use this formula. So the voltage you can apply is 1/4 watts times resistor is 10 to the power 4 ohms. So square root of 1/4 is a half, square root of 10 to the 4 is 10 square, so 50 volts. So you apply more than 50 volts and that thing will burn up. A heater is being designed that uses a coil of 14 gauge nichrome wire to generate 300 watts using a voltage of 110 volts. How long should the engineer make the wire? Okay, so look up the diameter of the 14 gauge wire.
.0641.
1.628
Hmm?
millimeters.
That's in inches.
Yeah, 1.628 millimeters.
Okay. So power is V square over R. R is V square over P. And resistance is resistivity length over pi R square. Okay. So the length of the wire is V square pi R square, power over resistivity. So the length of the wire you need is V square is 110 volts square. Pi R is 0.814 millimeters. Power is 300 watts. And nichrome, resistivity of nichrome. So nichrome resistivity is 1.5 times 10 to the minus 6. All right. Let's take care of powers of 10. That's 10 to the minus 6. That cancels with that. Okay, so it's 110 square times pi times 0.814 square and 300. And this should all work out to meters. All right. All equal to 56 meters. So for this heater, you need 56 meters of the nichrome wire. 56 meters is roughly the length of this building down that hallway. And remember, you need that wire, and then you have to wind it and put it in a small package for the heater. So an alternate to CFL, compact fluorescent bulbs, and incandescent bulbs are light emitting diodes, LEDs. Okay, so those old kind of bulbs, incandescent bulbs, they were about 5% efficient. What does that mean?
For every 5, I guess, for every 100 joules of work, you only got 5 joules of energy.
Yeah. For 100 joules of electrical energy, only 5 joules. Yep. Fluorescent bulbs are about 40% efficient. LEDs are 90 to 95% efficient. Okay. So even though LEDs are expensive, over time, you save the money. And in addition, these guys, the light quality deteriorates over time. This guy doesn't. Okay. So all the big manufacturers replace these. I mean, these manufacturing companies that needed bright lighting from high ceilings and stuff like that, they would spend a ton of money, maintenance and stuff. They all switched over to LEDs 10, 15 years ago. All right, so a 100-watt incandescent bulb can be replaced by a 16-watt LED bulb. Okay. Both produce the same amount of light. So 16 watts, that's the electrical energy being used. So this bulb that is using 100 watt of electrical power is producing the same amount of light as a 16-watt LED bulb. Okay. Assume the cost of electricity is $0.1 per kilowatt hour. How much does it cost to run a bulb for 1 year if it's run for 4 hours a day? Okay, so the 100-watt bulb, so the incandescent, so it's 100 watts of electricity, 4 hours, and it's 365 days. And so the energy used is that. And we'll be smart about this. This is 365. Okay, so this is 4 hours. Okay. A kilowatt hour is, this is 36.5 kilowatts. So this is 36.5 kilowatts times 4 hours. So it's 36.5 times 4 kilowatt hour. Okay, so that's 73,146 kilowatt hour. And so the cost is $0.1 per kilowatt hour into 146 kilowatt hour. $14.60. So the incandescent bulb is that much. And for the LED bulb, all you have to do is replace this by 16 watts. So we'll divide this by 100 times 16. So you can see that if the LED bulb costs even $12, it's worth buying it. So that's the kind of calculations that would go in there.
That's only for 4 hours a day.
Yeah, so,
Very old for later.
Linear,
huh?
it would be linear, so
Mhm.
even if it was 24 hours, it'd be the same ratio.
No, so if it was 8 hours a day, then you would save $24 a year.